This is our video for Unit 2, Day 5. Over systems of equations. So we're going to look at what systems of equations are and how we can come up with solutions for those systems of equations. Okay, so a system of equations or systems of equations is any time we have two or more linear equations. In this case, we're talking about systems of linear equations. So two or more linear equations using the same x and y variables. Okay, and so since we are doing two systems of equations using the same x and y variables, we can have two equations that would graph as lines, and they use the same graph. And so this is something that we're going to look at. We're going to look at how to solve, and there's a lot of different ways we can solve a system of equations. So we're going to look at the main three in this unit. And so first, we're going to look at solving by graphing. Okay, we're going to solve by graphing. And so our first example is going to be this. I'm going to give you two equations. So when we get a system of equations, you'll see two xy equations. In this case, they're both going to be in slope-intercept form. Y equals -3 over 2 x plus 1. And our second equation is y equals x minus 4. And to solve by graphing, we're going to first graph both equations on the same xy plane. So I want to make some y-axis and an x-axis like this. And we're going to graph both lines on the same graph. And so I'm going to identify my slope and y-intercept here. We're going to start with our y-intercept. If you'll remember back to the last couple lessons, when we graph, we start with our y-intercept. So for our first equation, I'll graph it in red, our y-intercept is 1. So I'm going to go to the y-axis and put a point at 1 on the y-axis. So if you need to pause at any moment to copy this down, go ahead and do so. And then I need that rise over run, or slope, to find my second point. So from this point at my y-intercept, the -3 rise tells me to count down 3, and the +2 on bottom tells me to count to the right 2. And I could do that a series of a few more times if I needed to. Or we could flip the negative to be your run. In that case, I would count up 3 and to the left 2, and that would still follow the same linear path. So there is my first line. We're going to graph the second line. Again, I want to identify the y-intercept and the slope. The y-intercept b, if these are in slope-intercept form, y equals mx plus b, y equals mx plus b, is -4. That's our slope, or our y-intercept. So I'm going to put a point down here at the y-intercept of -4. And then my slope, there's no number in front of the x. Remember that that means my slope is 1, or 1 over 1 for rise over run. So I'm just going to go up 1 over 1 as many times as I need to get a good linear graph. And you'll see that these two lines cross at this point. What that tells me is that at this location, the x-coordinate and y-coordinate would make both of these equations true, because the x-coordinate and y-coordinate represent a point that is on both lines. That's the solution to a system of equations. So we're going to write that down. The solution to a system of equations is the value of the variables that makes all equations true. Okay, it satisfies all equations, or makes them all true. And we could have lots of different kinds of solutions. In this case, when the two lines cross, there is only one solution. Okay, there's only one solution. That's the ordered pair, 2 for the x value and -2 for the y value. Okay? Most of the time, we're only going to have one solution, all right? If the two lines cross in any way, so if I graph two lines and they cross like this, there is only one solution. Now, if I graph two lines and they are parallel, meaning they never cross, then there's no points that make both of them true, and so there is no solution, or 0 solutions. And then if we have two lines that actually end up different equations, but when you graph them, they end up being the same line. So, and that seems kind of obscure, but if I get two different equations, but the numbers would simplify to where they're actually the same line, we say that there are infinitely many solutions. Now you'll see SOL as my abbreviation for solution. Okay, there you go, in case you couldn't see that. So that describes the different ways we can have solutions to a system of equation, but this statement here helps you understand that. The solution to a system of equations is the set of points or point that makes all the variables true for both equations. Okay, let's do another example. I've got some room left on my page here. We're going to do another example. We're going to solve by graphing. So I'm going to go ahead and make my axes here, y-axis and x-axis. You can make yours to match. And here are your two equations we're going to use. There's the first equation, y equals -1/4 x plus 3. And the second equation is y equals -2x minus 4. Now these are both in the same xy axes, so they use the same x and y values. And we're going to see where these two lines cross, if they cross, and that will be their solution. And so we're going to write down slope and y-intercept again. Slope of this line is -1/4, but the y-intercept is 3. And then for our other line, the slope is -2, and the y-intercept is -4. Now, for the slope of -2, we want to make it a fraction over 1, so we can do rise over run. So we're going to graph these first. I'm going to use red for this first line. I'm going to start with my y-intercept. I'm going to put a y-intercept of +3, and then I'll use this slope, rise over run, to find another point. So I'm going to rise -1, so I'll actually count down 1, and to the right 4. And I almost have enough room to do it again that way, but remember, down and to the right is the same as up and to the left, if you're keeping track kind of in arrows. So I can go up and to the left 4, so up 1 to the left 4, and I still end up in that same linear pattern. Sorry, I'm going to try and draw without a straight edge, not a good idea always. Okay, now I'm going to graph the second line. My y-intercept is -4 all the way down here, but my slope is down 2 to the right 1. Now I really don't have room to go down 2 to the right 1, but remember, that's the exact same as up and to the left. So down and to the right is the same direction as up and the left. So I'm going to go up 2 to the left 1, and I can keep following that pattern. And then if I try to work backwards, you'll notice it goes down 2 to the right 1. So I'm going to keep doing that, and what I notice is that these two lines cross all the way up here in quadrant 2. Remember, this is quadrant 2, right here at that point. Well, that point has an x value of -4, and it has a y value of +4. So the ordered pair for that point is -4, 4. So the solution to my system, I'm going to write it again for you here, is negative 4, comma 4. That's the one point where the two lines cross. So that's your solution. Okay, we're going to do a couple more examples because we can solve by using other methods. So we're going to go ahead and turn to the back. And we're going to do another couple examples on the back here. So this is what I want you to write down next. Okay, I've got two equations here, a system of equations. I've got two equations using the same x and y. But you'll notice the second equation is not in slope-intercept form. Remember, slope-intercept form is like that. Now, I could change this bottom equation to be slope-intercept form and graph it, but I want to teach you another method for solving systems, and that's using something called substitution. And so here's what I want you to realize. In order to do substitution, at least one equation has to have a variable all by itself. And if we want to make a note of that over here, we can. To use substitution, at least one equation must have a variable isolated. That means all by itself. So we've isolated y here. It's all by itself. Because I need to understand this, that when I say y equals 4x minus 3, what that means is y is the same value, same number as 4x minus 3. Okay? So that means that any other y could be replaced by an equal value. That's the concept of substitution, replacing something with an equal value or set of values. So since y equals all of that, I can replace this other y with that value. And so we're going to do that. Okay? So I'm going to take this bottom equation and rewrite it, 4x minus y, but instead of minus y, I'm going to replace y with this equivalent expression, 4x minus 3. And then I'm going to finish my equals 3 here. So all I've done is I've rewritten my equation with an equivalent value for y. This parentheses is where y used to be. And then we're going to solve this. Well, when we have a parentheses and a minus in front, remember that that minus sign is to be distributed to both of these. Not a 4x, we're not multiplying, we're just taking a minus to both. So my equation looks like this now. 4x minus 4x, and then this minus negative 3 is plus 3. Well, we've got a little bit of math to do here, a little algebra. When we combine our like terms here, 4x minus 4x actually cancels. So my equation works out kind of strange here. I get an equation that is 3 equals 3. That's a true equation. No matter what x is, 3 has to equal 3. There's no variable in there anymore. This is a special case. When I get this, when I get a true statement, you might remember from Unit 1, what this means is that any real number will work for x and y. In that case, we can say that this has infinitely many solutions. These are actually the same line. If I graphed both of these, they would be the same line. All right, we're going to try one other example here. Okay? In our next example, we will get an actual solution. We're still going to solve by substitution here. I'm going to abbreviate just because I'm running out of room. We're going to solve by substitution. Here are your two equations. First, y equals x minus 1. And in our second equation, sorry, I wrote that wrong. Let me fix that. In our second equation, we're actually going to start off with 5x plus, plus 8y. Sorry, I'm looking at my copy over here trying to make sure I'm doing it right. Equals negative 21. So we have two equations here. One we have solved for y. One is in slope-intercept form. I could graph that. But this one is a lot more difficult, and graphing it won't really work out very well, okay? Because the numbers just aren't very nice for graphing. So it's a good thing we have another method here called substitution. So what we have is a situation where this y value always has to be the same as 1 less than the x value, where I take x and I subtract 1, and that's how I get my y value. Well, that expression then can replace any other y value in this system. So it can replace this other y. So we're going to rewrite that second equation where we've replaced y with this expression. So I still start off with 5x, because I'm leaving that where it is, plus 8, and anytime I substitute, I use parentheses. So I'm going to put in my x minus 1 instead of that y, and then it equals negative 21 still. Well, now I have an equation that only has x's in it, and I can solve that equation for x. Distribute first. So 5x plus 8x minus 8, 8 times negative 1 is minus 8, equals negative 21. Now we can combine like terms here and here. 5x plus 8x, we're going to combine like terms. That's 13x minus 8 equals negative 21. And then if I solve this for x, I'm going to add 8 to both sides. So 13x equals negative 21 plus 8 is negative 13. So then just divide both sides by 13 to finish solving for x. Negative 13 divided by 13 is negative 1. So all of that work gives us an x value of negative 1. These problems are going to take more time, though, because a solution to my system of equations needs 2 variables. If there are 2 variables used, I better have 2 equations to find them. So I need to go back now into either one of these original equations using an x value of negative 1 and find out what the corresponding y value is. So I'm going to use this first equation because it's a little easier to use. I don't have as many numbers. So I'm going to go back here and rewrite this equation, y equals x minus 1, but instead of just using x, I know a value to use, negative 1 now, for x, and still minus 1 from that. So negative 1 minus 1, those don't cancel to 0. Negative 1 minus 1 is negative 2. So y equals negative 2 whenever x equals negative 1. So we're going to put those points together as an ordered pair. The x coordinate has to go first, then the y coordinate. And that is the solution to that system of equations. Okay, we're going to do some more examples in class, but this at least gets you a view of how to solve systems using a couple methods here. And hopefully with what we explain in class, it makes a little bit more sense.